This presentation is one of a series dealing with cargo operations on board an oil tanker. In this module, we deal with the task of measuring cargo quantity and handling different units of measurement. Our vessel has reached her destination. It is the task of the chief officer to determine the quantity of cargo on board as accurately as possible, to the satisfaction of the charterers and the other parties involved. The vessel carries a huge volume of cargo, contained in 7 cargo tanks and 2 slop tanks. The volume and weight of the cargo needs to be calculated tank by tank. The capacity of each tank is known, having been calculated by the shipyard, and can be found in the so-called ullage tables. The ullage tables use the ullage measurements obtained from the tanks. Knowing the ullage will give the volume of the tank contents. The ullage is the distance from the surface of the oil to the measuring point on deck. In our vessel, each cargo tank has a Saab level transmitter which measures the ullage very accurately. Radar signals are sent down into the tank and reflect on the surface of the oil. The ullage is shown digitally in the cargo control room. Before discharge, the ullages are often checked manually. Here there are 2 measuring points in the aft ends of the tanks, port and starboard, each fitted with globe-type vapour control valves. Using a special electronic ullage tape, so-called MMC, you can measure the ullage without opening the tanks to the atmosphere. Here you are taking the ullage in centre tank number 4, port side. The cap is removed and the MMC fitted. The vapour control valve is opened and the tape lowered into the tank. When the surface of the oil is reached, you will hear a steady signal. The ullage measurement is 206 centimetres. Remember for the moment that the vessel has no list and is on an even keel. Use the tables at the end of the ullage tables, which give you volumes at every 5th centimetre at an even keel. You have to interpolate to find the volume of 206 centimetres. Find volumes at 205 centimetres and 210 centimetres. At 205 centimetres, this is 23,013.7 cubic metres, and at 210 centimetres, 22,963.4 cubic metres. The difference in volumes is 50.3 cubic metres. Divide by 5, and you can see that every centimetre equals 10.06, or let's say 10.1 cubic metres. Our company standard is to calculate ullage to the nearest half centimetre. Every half centimetre is 5 cubic metres. As 206 centimetres ullage is less volume than 205 centimetres, deduct the difference of 1 centimetre, 10.1 cubic metres, and you get 23,003.6 cubic metres. The position of the measuring points in the sides of the tanks is far from ideal. The tanks are wide and the measuring points are away from the tank centre, so there will be a big difference if the vessel has a trim or a list. That is why you should try to load the vessel on an even keel and with no list. If there is a trim or a list, you must use the corrections. On this occasion, let's say our vessel has an aft trim, a positive trim of 1 metre, and a port heel, a negative heel of 1.3 degrees. The ullage is still 206 centimetres. Note the separate correction tables for ullages taken, port and starboard. There are similar tables for corrections for the level transmitters. This is the correction table for cargo tank number 4 and the port measuring point. At even keel and with no list, the correction is 0. Starboard side always has a correction. In this vessel, it is more convenient to take ullages on the port side. Let's work with our ullage of 206 centimetres and the given trim and heel. Interpolate between 200 and 210 centimetres, or 2.0 and 2.1 metres, as shown. In the table for 2 metre ullage, move across to the positive 1 metre trim column. Note the readings for negative heel, 2 degrees and 1 degree. These are 0.584 and 0.314 respectively, a difference of 0.27. Do the same thing in the table for 2.1 metre ullage. In this case, the same factors are obtained, so the difference is the same and no interpolation for trim is required. Note this is not always the case. But now we must allow for the heel of negative 1.3 degrees. Divide 0.27 by 10 and you will get the value of every 1/10 degree of heel. Multiply by 3 and add to the negative 1 degree trim factor. The result is a positive correction of 0.395 metres. Add this correction to your ullage reading of 206 centimetres. You will get the correct ullage, 245.5 centimetres. Quite a difference in volume. Be careful with trim and list. The volume of oil in the tanks changes with the temperature. The volume increases with higher temperatures. To be able to calculate the weight of the cargo, you must find the correct temperature of the oil. A difference of 1 degree temperature is about 400 barrels in our vessel. The difference in a ULCC can amount to 1,000 barrels. That's a lot of money. To be able to find the weight of the oil, you start by reducing the measured volumes to a standard temperature of 60 degrees Fahrenheit, or 15 degrees centigrade. So a volume measured at 85 degrees Fahrenheit must be reduced to a net volume at 60 degrees Fahrenheit. To do this, we use the reduction tables, the so-called ASTM tables. We will return to this in a moment. Your immediate problem now is to find the accurate temperature in each tank. After a long sea voyage, there will be layers of different temperatures in the tanks. Every tank should be measured and calculated separately. Measure the temperatures to the nearest half degree. Here we use the multifunctional MMC instrument, this time set up to measure temperature. Temperatures are taken at 3 different levels: a quarter, a half, and 3/4. Depending on equipment available, the routine may be different on your ship. The ideal position to measure the temperature is close to the tank centre, but with no vapour control valves here, we have to be content with the temperatures taken at the aft end of the tanks. The average temperature in cargo tank number 4 is found to be 85 degrees Fahrenheit. The volume of the cargo at actual temperatures is the total observed volume, TOV. From this volume, you should deduct eventual free water, sediment, and non-segregated slop. You now have the gross observed volume, GOV. All tanks need to be probed for free water. The MMC instrument is used again to find the interface between water and oil. The surveyors in this port prefer to use a sounding rod smeared with water-finding paste. The rod is snapped onto the tape of the MMC and lowered to the bottom of the tank through the vapour control valve. The paste will change colour when in contact with water. To find indications of water, spray the rod with grease remover or kerosene. Now find the volume by using the special innage table. To calculate weight of cargo, the oil industry mainly uses API gravity at 60 degrees Fahrenheit, or alternatively, density at 15 degrees centigrade as standard units of measurement. The loading orders for this cargo were given as API at 60 degrees Fahrenheit, so use this unit and long tons while working with this cargo. First, convert this gross volume to a net volume at a standard temperature of 60 degrees Fahrenheit using the ASTM tables. Remember that the temperature of the cargo is the most important factor. Economically, finding the correct cargo temperature is more important than an absolutely correct API or density. The temperature of our cargo is 85 degrees Fahrenheit, and the API of the cargo is 26.8. Use volume 1 of the ASTM tables. Find table 6A. Against API 27 and a temperature of 85 degrees Fahrenheit, you find the factor 0.9892. Do not try to interpolate. Use the closest figure. Next, use volume 11 and 12. In table 11, you will find a column long tons per barrel at 60 degrees Fahrenheit. Against API 26.8, you'll find the factor 0.13955. Multiply the two factors found, and you will get a general factor of 0.13804286. Now it's necessary to convert cubic meters to US barrels. Use table 1. Multiply the gross volume obtained from the ullage table, 23,003.6 cubic meters, by the factor, in this case, 6.28981. You will get 144,688.3 barrels, which when multiplied by the general factor gives 19,973.2 long tons. If you want to know the weight in metric tons, you multiply by factor 1.01605, also found in table 1. All cargo calculations must be done with speed and accuracy. Using general factors will save a lot of time. Observe that you could have used 3 factors instead of 2 to get a general factor, directly giving you long tons from cubic meters. Of course, it's possible to work the other way round. Divide long tons with the general factor, and you will get cubic meters. A quick look at the ullage table will give you the corresponding ullage. If the same cargo were given in density, at 15 degrees centigrade, and with the temperature measured in centigrade, you would have worked in cubic meters and metric tons. You should never jump between API and density. We will do this conversion only as an example. We use the ASTM tables to convert API to density and Fahrenheit to centigrade. First, the gross volume is reduced to net volume at 15 degrees centigrade. Use ASTM table volume 7 and consult table 54A. Do not interpolate. Next, we use table 56 in ASTM table volume 11 to 12. Here we have to interpolate. Every tenth is worth 0.1. The general factor is 0.8823. Multiplying the gross volume with the general factor, we get 20,296.1 metric tons. This kind of conversion will always differ. Stick to what you have and only convert from long tons to metric tons, from barrels to cubic meters, and vice versa. When the cargo is discharged, all tanks will be searched for remaining cargo on board, ROB. The tanks will be dipped only in the aft part. The special sounding rod fitted to the MMC is used. Too often there is discussion of ROB even when the indication on the sounding rod is less than an inch or a few centimetres. Most likely there is unpumpable mud or sediment in the end of the tank. This layer may be penetrated and a thin layer of oil smears the rod. Your job is to prove that the findings are negligible, unpumpable, or out of reach of the vessel's pumps. It's a good idea to use a rod with a flat end to avoid penetrating the sediment. In this vessel there are only vapour control valves in the aft end of the tanks. If there is a discussion about ROB, and the dip clearly indicates liquid, use the wedge formula or wedge table to calculate remaining cargo. If the dip indicates sludge or sediment, you should also suggest using the wedge formula to compute ROB. If the representatives from the terminal don't accept this and force you to open the inerted tanks to the atmosphere, you should dip the tank in as many positions as possible. The fact that you are forced to open tanks to the atmosphere should be noted in the ship's logbook, and a protest should be filed. The results, as well as positions dipped, and the time must be carefully noted. If these additional dippings don't show any volumes left, the tank should be regarded as empty. If there is sludge or sediment found in the tank, take an average and use the innage table to find the volume. If there is a volume of oil in the aft part of the tank and a layer of 1 centimetre sludge or sediment is found in the most forward part, it's reasonable to argue that 1 centimetre of sediment covers the whole bottom and should be deducted from the volume of oil left. Disputes on ROB are very common. You should never allow the loading arms to be disconnected until you know that there are no such claims. You should always be prepared to start the pumps of the vessel in order to show that disputed volumes are unpumpable or out of reach of the cargo pumps. Before the vessel arrives at a loading port, the slop must be measured and its weight calculated. But finding the interface between water and oil can be a tricky business. The task is to find the ullage of the interface. Again, we use the MMC through the vapour control valve. When the sensitive sonde is lowered through oil, you hear the steady signal, indicating oil. When the sonde reaches water, the sound changes to an intermittent signal. Remember that there is no sharp interface between oil and water in a slop tank. Usually there is a layer of an emulsion of oil and water. But with care you should be able to establish safe volumes of slop and water. The difference in volumes will give you the gross volume of the slop. The importance of finding the volume of the slop is to establish what volume of clean water remains under the slop oil. Next, you must find out the quality of the slop. Here, a half-litre sampler is used attached to the MMC. A sample is taken from the centre of the volume and poured into a clean sampling glass. A hydrometer is slowly lowered into the sample and is allowed to float freely in the oil. The actual API is read from the hydrometer. Temperature is also taken. In this case, both API and temperature can be read from the hydrometer. To find the weight, reduce the volume to the corresponding volume at 60 degrees Fahrenheit. Use ASTM Table 5A to convert measured API to corresponding API at 60 degrees Fahrenheit. A final point about using the MMC. It is bad practice to leave it unattended while fitted to the vapor control valve. The valve can close and damage a very expensive instrument. Measuring cargo should be done by an experienced officer. Great care should be taken to record results, times and methods used. These are valuable facts to use in any dispute on cargo quantities. The volumes given by the ullage tables are seldom exact. When you load the vessel, you will, most of the time, experience differences between your own figures and shore figures. Your problem is to take on board a full cargo without overloading nor short-loading the vessel. To be able to do this, you must know the vessel's experience factor. Different companies and charterers use slightly different methods to compute this factor. Principally, it is the ratio between ships and shore figures obtained by comparing the results of a number of actual loading operations. Remember, measuring cargo is not an exact science, but professional skill and good routines will certainly save a lot of money.